In this lecture, we will take a look at some more advanced sorting algorithms.
The first algorithm we will talk about is called shell sort. The shell sort algorithm was actually named after its inventor, Donald Shell. This was actually one of the first algorithms that break that O of n squared time barrier. All the algorithms we talked about so far took O of n squared. This one's actually faster than that. The key observation was that to get an improvement in the running time, we can't just keep comparing adjacent elements. That's going to take way too much time. Instead, this algorithm actually compares distant elements. So, for example, maybe we would compare every 5 elements and then every 4 and so forth. But what we do is we compare distant elements, and then with each iteration, we actually decrease the amount of distance between the comparisons of elements. So like I said, maybe we would compare every 5th element with each other, and then every 4th element, then every 3rd, or so forth. But we keep doing this until we get to the last phase. In that last phase, we are comparing the adjacent elements. Now, what happens here is those elements are so close that the amount of time it actually takes to sort those elements is a lot smaller compared to any of our previous sorting algorithms. And for this reason, the shell sort algorithm is sometimes referred to as the diminishing increment sort algorithm. The key thing about shell sort is that it uses a very specific sequence, which we'll denote as H1, H2, H3, all the way up to HT. This sequence is called the increment sequence. Now, the thing I'll mention about this sequence is that any increment sequence will work, just as long as H1 is 1. Now, what we will see is that some choices for these different values in the sequence are better than others. So the way we would think about this sequence is first think of the array as these sets of elements. And let's say each set contains elements that are HT apart from each other. So if you think about your array, group up the elements that are so far apart from each other. In this case, we're denoting that as HT. We then sort these elements in each set. So the resulting array is not actually sorted, but with respect to those separate sets, they are sorted. So we say that this resulting array is HT sorted. We'll then go to HT minus 1. So now we can think of the arrays being partitioned into these groups that are HT minus 1 apart from each other. And then we sort those elements. So then that means it would be HT minus 1 sorted. Now, how do we get HT minus 1? We would get some type of increment. So we're going to note that as HK, which is actually a function of HK plus 1. So we're actually going to do this function that gets us from HT to HT minus 1. And then we'll use that same function to go from HT minus 1 to HT minus 2, and then another function that lets us go from HT minus 2 to HT minus 3. So this sequence is the result of a function where we start at some number, and if we keep applying this function, we will eventually get to 1, which will be the value of our H1. But we'll do an example just a little bit, but the idea with this is we sort the array by these specific sets, and then we'll decrease the gap between the elements that we sort. We decrease again and again and again, and eventually the gap is just going to be one element apart. Let's do an example just to show how we would use this algorithm. So let's say this is the array that we want to sort. Clearly it's not sorted, but we'll take care of that. So what we're going to do is that for our first sorting procedure, the first part, we want to 5 sort this array. And what that means is we're going to take the elements that are 5 apart from each other, and we'll sort those elements. We'll start by sorting A0, A5, and A10 because those elements are 5 away from each other. So what we find here was the 35 was at A5, and that's the smallest, so we move that to A0. The 41, which was at A10, is the second value, so we put that to A5. And since 81 is the largest, we move that to A10. So now among this set, it is sorted. We'll now do the same thing for A1, A6, and A11 because those elements are 5 apart from each other. So we had 94, 17, and 75. We sort those, so we put 17 in A1, 75 in A6, and 94 in A11. We'll now sort A2, A7, and A12. So we're going to sort 11, 95, and 15. So we see that after we sort it, 11 goes into A2, 15 goes into A7, and 95 goes into A12. We'll next sort A3 and A8 because they're 5 apart from each other. There's no A13, so there's nothing else to include in this set to sort. So here we had 28 and 96, so that means we would put 28 in A3 and put 96 in A8. We'll then sort A4 and A9 because they're 5 apart from each other, and in this case 12 and 58 were actually in that same order, so we didn't have to do any swapping. But now that we've done all these elements, we say that the array is 5 sorted. We'll now do the same thing, except we're going to 3 sort the array. The idea is that we sort the array by some gap, and then the next time we do a smaller gap. So this time we'll 3 sort the array instead of 5 sort. So here we'll sort A0, A3, A6, A9, and A12 because those elements are 3 apart from each other. So when we do that, we would see that we would put 28 in A0, 35 in A3, 58 in A6, 75 in A9, and 95 in A12. We'll next sort A1, A4, A7, and A10 since they're all 3 apart from each other. So we see that we put 12 in A1, 15 in A4, 17 in A7, and 81 in A10. We then sort A2, A5, A8, and A11 because all those are 3 elements apart from each other. So we get the 11 in A2, 14 goes into A5, 94 goes into A8, and 96 goes into A11. So now we see that this array is 3 sorted. So now we have the array 3 sorted, and it's also 5 sorted. So let's say now we want to 1 sort this array. How can we do that? Well, we can now use insertion sort because the smaller elements are closer to the left and the larger elements are closer to the right. Are they exactly in the right spots? Close, but it's a lot better than our original unsorted array. So what this does is it actually cuts down the number of movements and swaps that we have to make. As a result, this is the resulting sorted array.